For today's lesson, we're going to be talking about electric fields and voltage. We're going to start using voltage more and more as we explain more and more phenomena. But what is voltage and how are we going to measure it? That's what we're after. The only way we're really going to understand voltage is to make sure that our understanding of electric fields is solid. So let's go over a few of the items that we already know. We'll start with the most basic. In fact, in physics, especially mechanics, we normally start with F equals ma. Let's do that. So we know for sure that a force causes a mass to accelerate. And one of the formulas that we're most comfortable with is weight equals mg. Why would we use g? Because that's a g field, and that helps us understand our E field. So another version of that is I can end up writing weight equals mass times gravity. Forces cause masses to accelerate, and we could say weights are masses in a gravitational field. Now, if we end up talking about electric fields instead of a G field, we can end up talking about an E field. So F equals QE. Here we've got charges instead of mass. Here we have an electric field instead of a gravitational field. But what is electric field? We started with Coulomb's law earlier, and we ended up with a statement where we could say where the electric field was equal to K, and that is our electric constant. So I can put a little E here if I'd like, and then that's going to be Q all over our distance squared. Now that distance squared is something that we've seen with gravity. We know that it's going to have that inverse squared law where things drop off rather quickly with distance. If we are using something that is around, maybe a point charge, just like on the Earth, I could end up saying the Earth is round. I can rewrite this formula as a different version. I could say E is really going to be equal to our K electric and our charge divided by our radius squared. Now, electric field is something that exists that's going to end up helping us with our forces. So if I were to take this formula and I were to simply put a Q on each side, multiply both sides by Q, we can get right back to Coulomb's law. So I could say QE is going to be equal to K, that's electric, Q, all divided by our radius squared. And now I've got Coulomb's law, K, Q, all over our R squared. If you recall, if we have two charges, they're going to put a force on one another. Why are forces important? Because fields don't make sense unless we're talking about things in that field where we can get a force. Now, voltage is going to be a little bit different. While we have this nice correspondence, we also have this other idea of voltage. And earlier we said that our voltage was equal to an electric field times a distance. Another formula that we have for voltage is we could say our voltage is equal to potential energy per charge. So we're going to bring all of these ideas together. But let's get back to our fields and our electric fields. I should say our forces and our electric fields. Let's take a quiz right now and see if we really have a solid understanding. Let me grab that for you now. For today's quiz, we want to know about electric field strength. I've got three different boxes, A, B, and C. Box A has a positive and a negative and a negative, essentially at a cross. I want to know what the electric field strength is at A as compared to B, which has two positives up top and a positive negative on bottom. How does that compare to C? If I had two negatives on top, two positives on bottom. How does the field strength compare at point A, point B, and point C? Here's what your quiz looks like today. I'll hold that up right now. As always, mark your answer as completely as possible and list your level of confidence. Typical student responses on this quiz are, I don't know what you're asking me to do. Give them some hints. Say, I would like to know the electric field at A, B, and C. They might say, I still don't understand what you mean by magnitude of electric field. Remind them that force equals QE. Ask them what that means. Most of them will be able to say, if I have a charge in an electric field, I feel a force. But then they might say, wait a second, I don't have a charge at A or B or at C to understand about the electric field. And then you might wink at them or say the magic word, well, maybe you need like a test charge, wink, wink, and they'll say, oh, wait, I got it. At that point, they'll start to give you answers such as, maybe they're all going to be the same. Every one of them, A, B, and C, have 4 charges. Right away, other students will jump in and say, that can't be true because, look, the charges are different. Sometimes there's positive, sometimes there's negative. I bet you they add up in different ways. At that point, most of them are going to end up saying, we need a little bit of time. It's probably a geometry problem. Give them a nod and then give them some time. If you like what we're doing here at the Idealized Science Institute, be sure to like, comment, and subscribe. And understand, this is just one of the many lectures in our Understanding Electricity series. Let's see if we can make some sense out of this. Instead of A, B, and C, I'm going to replace those points with a positive test charge. We'll remember that they're A, B, and C, but in this case, I'm going to put a little positive test charge right in the middle here. And a test charge is infinitesimally small. It doesn't affect the environment. It simply lets you know where the fields are. Maybe I can use a measuring device and draw an arrow of the same length each time. This positive encounters a force from that positive right there. It is going to end up pushing that test charge away, so maybe I can put a little arrow going down at that length right there. I'll just go around in a circle. That negative is going to end up feeling an attractive force. So in that case, we're going to end up having this blue force pulling on this red, and I can end up saying, well, it's going to have a force going up like that. And notice they're about the same size. This negative right here is also going to be pulling on that positive, so it's going to end up pulling it in the other direction, like so. And then we also had this other positive. It's going to end up repelling that positive up in that direction right there. And then right away, we can start to see that everything's going to cancel out. These two negatives are going to cancel out, and these two positives are going to cancel out. And if you'd like to do vectors, you can. I can add vectors by simply popping them off. I could pop off a red, and then I could add a blue to that, and then I could add another blue and another red. Let me do that quickly. I'll pop off, I'll just go in the same order again. If I pop that off down here, you'll see that I had a red arrow going up like this, and then I'll add my blue arrow to that. So that blue one would go in this direction, and I add vectors tip to tail, and then I'm going to end up having another red vector that I can end up coming right back down here, like so. And then when I put my last blue vector right here, I end up going right back to where I started. So my resultant vector is simply 0. So this cancels out completely. So A is not going to be the answer. We know that right away. So A is going to end up probably being the smallest. Let's take a look at B. Do the same thing. That little test charge there is going to feel a repulsive force from these three and an attractive force in that direction. So let's start off with this red up here. It's going to end up feeling a force down in that direction. This one is going to end up giving a repulsive force in this direction here. Try to make them about the same size. Come down here. This one is going to end up giving a repulsive force up in that direction. So right away I could see these two vectors are going to cross out. But the negative down here is going to add to this other red vector that we already had. So I'll draw another one. I'm trying really hard not to cross my reds and the blues. It hurts my markers. But you could see these two will cross out right away. And essentially what I'm going to end up having is a red and a blue. And I'll start right down here. I'll pop off that first red vector. And I'll say that comes down this amount right here. And I'll put that on there. And then I can add tip to tail this blue vector. And that blue vector is going to end up going in the same direction. So we end up with a resultant vector of essentially two of those arrows that I was starting with. So B is going to end up certainly being stronger than A. Now let's go over and do C. In this case, we're going to end up having two negatives up top, two positives on bottom. Well, the negative is going to end up giving an attractive force in this direction. So I'll put a little arrow up in that direction. That negative is going to pull on that test charge up in that direction, like so. Each of these positives are going to repel, but they're going to be going in the same directions as our blue. This positive would give another arrow going up here. Again, I'm trying really hard not to damage my markers. So if I end up having this positive, it's going to give a force up in that same direction there. Now you'll notice that we have all of our vectors going in an upward direction as such. Now what I can do is I can add those vectors. I can pop each one of these off. Let's start off with the red, and I'll start right at the beginning point right here. I've got a red vector here. And then I add this other blue vector to it. So same direction, but now look at the distance that we're going to travel. Now I'll add the red vector here up in the same direction here. Red, and then I've got my blue. And I think we're going to see a very, very long resultant vector here in a second, which clearly is going to show that I've got an overall resultant vector. If this one is about the length of that block, this is way longer. This resultant vector here is almost two of these blocks, and that is clearly going to have the greatest field on it. So we'd go C. I guess we need to put the C right here. C, and then B, and then A. That's your quiz for today. All right, now that we understand fields and we have an intuitive feel for this, hopefully you can start visualizing these. This is important because we know that an electric field acting at a distance gives us our voltage. That's one of the definitions. That's one of our primary ways we're going to understand voltage is through electric fields. We also have voltage as being potential energy per charge. Let's see if we can draw this out. If I were to take two plates, and maybe I'll make them more like gravity. We can leverage that idea again. Let's go ahead and draw a plate on the bottom and on the top. Let's just say we'll put our negatives on bottom here. So I've got some plate. And then up here I've got another plate. And maybe that one's got positive charges on it. So maybe I can use my red, and I'll put red for positive up here. And I'll put 1, 2, 3, 4. We'll just put 4 for right now, and then I'll also use 4 negatives down on the bottom here. I'll put a negative, a negative, a negative, and a negative. Now, clearly, if I had more charges, I would end up having more of a field and more force. I can end up drawing field lines down, and notice our field lines start at our positive and come down towards our negative. So I could have a field line here, I could have another field line here, and so on. And they look reasonably uniform. And let's just say they would go on and on and on. Well, this is how we're going to start talking about voltage. Imagine if I had a test charge here. And remember, test charge is going to be infinitesimally small. It's not going to make its own field lines. It's just going to be so small that it can feel the force according to that QE. If I put a test charge down here and it's essentially sitting on the bottom here, we would say the potential energy that it has is 0. And remember, potential energy per charge is going to end up being voltage. And potential energy, we could always end up saying, is our QED. And I still had my Q over here, so I could end up putting a Q right there. Notice the Q's cross out, so you could see how this formula goes right into our voltage equals electric field times distance. This has no distance. It does have an electric field. It's got some E field coming down. as I put a charge there, it will feel a force, but if that force is essentially at its lowest potential energy, nothing's going to happen. But if I raise that up, let's say that I raise this up right here and I put a positive right there, well, now suddenly it has a distance from right there. I've now raised it some distance. It has potential energy. It's no longer at zero, so I could say this one has a potential energy that is going to end up being larger than that. This is not equal to zero any longer. And in fact, as I go higher and higher, I'm going to add more and more energy to that system. That looks bad. So that is no longer equal to zero. As I were to put the charge, let's say over here and then over here, we can end up saying that each one of these has more potential energy per individual charge. And I'll put little circles around here, keep them consistent. So if I go around like so, okay, each one of those is going to have more and more potential energy. Also, another term for that is going to be voltage. More potential energy per charge, more voltage. Same electric field, at a greater distance, they've got a greater voltage. So I could say this one is going to end up having a big voltage. This one is going to end up having a smaller voltage, and then down here, we would say that voltage is equal to zero. And that's really what we mean by voltage, an electric field acting at a distance. Because we can say that it's really only about the distance or the height, however you want to define that, we can start calling these equipotential lines. In other words, anything that is at this line right here, we can say is at the same voltage. So this one right here would be at a particular voltage. This one would be at a particular voltage. And this one up here would be at a particular voltage. And so those lines going across would be called equipotential lines. And what they tell us is, where's the voltage the same? And that's going to end up being a really great way to start thinking about what voltage is. Voltage is going to be either position, or we could think of it as its energy that it's holding. Now, that's a really simple example. You have nice parallel lines. I wonder what it's going to look like if we start to end up having something for a point charge and we start moving out radially. I think I'm going to need a little bit of room here, so I might have to do a little racing. All right, let's start back with our equipotential lines. Start off with a few things we know. Let's just start off with Coulomb's law. That should be easy enough. F equals K Q divided by distance squared. If I were to just take these three values right here, that becomes our electric field. Electric field is simply going to be our K Q all over our D squared. Now, that D squared is instantly an inverse squared law. And we already know what that means. An inverse square is going to end up having some kind of graph that looks like it drops off very quickly. We're going to end up having some kind of drop off with our force as compared to our distance. But we want to talk about voltage. So if I've got my electric field here, switch markers, if the electric field equals KQ all over D, and this is going to end up being our, I think we needed to put that as our electric field here. And our electric field is going to be very similar to our force because we also have F equals QE. But if I ended up taking this E equals KQ all over. And remember, if I'm talking about round objects, I can talk about radius instead of distance. Let me modify that right here and use an r squared. Maybe I'll do a d squared first just to make sure that everyone is comfortable with that. So I'll put our d squared right there. Now, I can multiply the same variable on both sides. In other words, if I ended up multiplying this side by a d, I can also multiply that side by a d. That would cross out with one of our squared terms, and I would end up having just my k, my q, all over my d. Notice that's a d, not a d squared, and we know where voltage is now equal to our electric field times our distance. So our voltage is going to end up being not a d squared term, inverse squared, but a linear, or I should just say an inverse term. I want to end up using these for our radius instead. So I could say my voltage is going to be equal to my k, q, all over my r. And I could have put my electric field as electric field is going to be equal to k, q, all over my r squared. Well, this inverse right here, this voltage is proportional, so I could say my voltage is proportional to 1 all over the radius. If I have that, I should start being able to maybe make a new kind of graphic. Now this one, we know it's going to drop off the inverse squared, but what about the voltage? So maybe we can make a little t-table right here. I think it'll be appropriate to do it right here. Let me use a ruler. Make it look neat. And then I should have enough room over there to draw. So let's do 5 values, we'll say. So I'll start all the way up here, come down here, and I'll put a mark. Let's talk about our voltage and our radius. So I could say if I have a particular, let's see, what do we want to do? We'll do radius at first. We'll do, for any given radius, what would the voltage be? And I could simply use my 1 over r squared. So if I ended up just using our first 5 values, let's use a radius of 1, 2, 3, 4, and 5. So how does our voltage change with our radius? Well, right away I could put, for r, I could put 1. So I end up having 1 over 1, and that's just going to be 1 volt. So if our radius is 1, our voltage is 1. If I were to put a 2 in here, well, I'm going to be down to 0.5. And then if I had 1 over 3, that's 1/3, 0.33. 1 over 4, which would be 0.25. And then 1 over 5, which would be 0.20. So I should be able to make a quick graph of that. And let's go ahead and plot what that looks like. Maybe I can squeeze it. Well, I guess I'm going to have to do some erasing again, but whatever. Let's go ahead and just graph this out. I'll just make a quick little graph, and I'll go from here to here. And I'll put my radius as 1, 2, 3, 4, 5, and I'll start at 0 here. And then for my voltage, it looks like I only go up to 1 here, so let's go ahead and just start with that. This would be our 1 right here. This would be our 0.5, and then I could do my 0.25, 0.75. So I could say, if that's 1, this would be 0.5, and that would be 0.25, and that would be 0.75. And this would be our radius, and this would end up being our voltage. So if I had my voltage right here, let's go ahead and put those points on here. I've got, for a radius of 1, I'm up here at 1. Marker is dying. And if I were 2, I'd be at 0.5, so I'd be somewhere right here. 3, I'd be at 0.33, so that's probably about here-ish. 0.4, I'm sorry, at 4 I'd be 0.25, and at 5 I would be at 0.20, which is a little bit less. So I'm going to end up kind of dropping off, and that marker seems to be just about dead, so I'm going to have to get another one. Something like an inverse function, which is going to be the general shape of an inverse squared, but maybe a little bit less pronounced. So we end up having that inverse value, but there's a way that we can end up drawing this for, let's say I have a positive right here, and I'm going to put some positive charge right here. And what I want to end up talking about is the equipotential lines. In other words, where is the voltage going to end up being as I go out from this particular point? Let me see if I can rearrange things. All right, I might have gotten myself into a little conundrum here with board space. I might move this over a little bit, but I think what I'm going to do is I'm just going to force this up here. I like the size of this graphic, but I'm going to make it a little bit smaller over here, because here's the plan. I'm going to end up, instead of having a set radius, I'm going to put a set voltage. I'm going to make another one of these tables here. Instead of making another graph, I'm going to use my equipotential lines as my graph. All right, let me just try this, and I can always try to move that if I need to. Let's make a smaller T-table, because I'm going to need some room over there. I'll start up here, and let's just go 5, 10. And mark these. All right, here what I'm going to do is, instead of having my voltage is 1 over the radius, I could say, well, if the voltage is proportional to 1 all over the radius, I can also just flip them, and I could say the radius is proportional to 1 all over my voltage. So in this case, I'm going to set my voltage, and I'm going to calculate the radius that it's at. And I'll do the same thing I did here. 1, 2, 3, 4, and then I'll do 5. Put some little lines across here. All right, so if my voltage was equal to 1 here, this would be 1 right here. So I'd have 1 again. And then if I put 1 over 2, it would just be 0.5. So the numbers are going to be the same. So 3 would just be 1 over 3, 0.33. And 4 is 0.25. And 5 would be 0.20. Now what I want to do is I'm going to move this over just a little bit, because I'll normalize this to be 1, and that will be a meter, and I think I'll be able to just barely squeeze that on here. Let me get my red, put it over here, maybe down a little bit lower. So in other words, let's say that I had some positive charge there, and then I wanted to figure out what would the voltage be as I moved away or moved closer. You could do it either way. If I used a positive test charge, remember, I'm going to have to do work. If I had a positive test charge all the way out at a meter, and then I push it in here, I'm going to end up doing work to get it to stay there because it wants to go away. It's going to feel a force. Let's go ahead and see if we can put these lines on here, and I'm going to do them to scale. So I'm going to use a little trick. I'm going to end up using my meter stick, get my values here. So at 1 meter, and that's really far out there. Let me move this over just a tad bit. All right. I'll put this down here. So I'll put my positive right here. And then I can start all the way out at the 1 meter mark, which is essentially going to be as far out as I can go. And if I were to put a positive test charge, this is going to end up being, we'll say, the 1 meter mark. So I'll put this all the way out here, and it's going to be pretty close. So I'll end up saying anything on this line right here is going to be an equipotential line. Now imagine that goes all the way around like so. I'm not going to bother doing that. I could then go for my voltage of 2 volts. So right here, this is going to end up being our voltage equal to 1. So I'll put voltage is equal to 1 right there. Now, our voltage at 2 is going to be at the ½ meter mark. Get my meter stick here. About 5, like so. Put this in here. And we'll see that our equipotential line for our voltage equaling 2 would be right there. And then 3 would be a third. Got my meter stick. Put it right here. And this should give us a better understanding of what those equipotential lines are really going to show. This is, I think, a better system than showing our inverse. So this would end up being about a voltage of 3. So here I've got my voltage equal to 3. Our 4 would be at 0.25, so it's getting a little bit smaller. And they're going to start stacking up more and more. 0.25, right about there. So here I've got my voltage equal to 2 volts. And then 1 would be at, oh wait, did I go the wrong way? This is 4 volts. Because it's going to take more and more energy to get it closer. So that's our voltage of 4. And we'll just use units of volts again. And this one has to be at 0.2. And I could go down further if I'd like. But I think you're going to get the general idea that these will be anything but linear. So if I put this one right here, they're going to start stacking together a little bit more. Oh, let me redo that one. That one looks pretty bad. I'll remeasure. Everything's easy till you try it. 0.2, about right there. You'll notice they're going to start getting closer and closer together. That one would be 0.5. Let me just make sure that's about right. That one was a little bit light, but here you could see our voltage. That's going to end up being 5 volts. Call that volts on each of these. You could see how they are going to decrease and they're going to start stacking up as we get closer and closer here. In fact, as my voltage starts to approach infinity, they're going to stack up, stack up, stack up until it almost touches here. So that's a way to start thinking of equipotential lines. Now what it means is if I had a positive test charge and I put it here, 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 anywhere along this line, it's going to still feel that 2 volts. But if I shifted it in, I have to do work in order for that charge to come in. Now it would do no work moving in this direction because work is a force parallel to a distance, and this would be going perpendicular. So in this equipotential line, the voltage is the same, and so it would take no work to be anywhere in that band, and so on and so on. So that's hopefully going to give us an idea of what these equipotential lines offer. They're a nice way to start thinking about energy levels within our distance. All right, but now we need to figure out how do you actually measure this physically, like experimentally. And for that, I'm going to need to clean up and get an apparatus in here. I was getting ready to erase everything, but then I realized how I was off by about 1.5 centimeters, and boy, did it really skew the look of this. So I just ended up drawing this 4-volt back to scale, and you could see how they start to build up, build up, build up. So it's not going to be linear like you might think. All right, now I'm going to erase everything. All right, let's show you how we experimentally measure voltage. It's not as easy as you think. We're going to have to use some magic things like an electron gun. And yeah, I said an electron gun, but that shouldn't be that silly at this point because we've seen a Van de Graaff generator shooting off electrons. So let's just start off with this, quote, electron gun. And an electron gun is simply going to look something like this. I'll just draw it as a square, and we'll say out of this thing we're going to end up, so I'll call it an electron gun, and it's going to fire electrons out of it, literally. So electrons are going to end up firing out of this apparatus. And why would they end up going anywhere? Well, out here I've got a big plate. Let's see, I'll put the plate here. I'll put it up here. Put a plate, something like this. And on that plate, I'm going to end up putting lots and lots of charges. So if I had a plate that looked like that, maybe I can end up putting positive charges on it. And positive charges are certainly going to attract these electrons. So I've got positives on here. And right in the center, I'm going to put a hole. And that hole is going to allow our electrons to go right through. So I'll put the hole right here. So as the electrons feel an attraction here, they're going to end up going right through that hole. Think about this. If you're an electron, you want to get to those positives. So you're going to end up, as it comes out, you're going to feel a force in this direction, and you're going to feel a force in that direction. Kind of like a slingshot. But again, these two vectors, if I pop one vector off, they're going to end up taking us in a straight line. So while these electrons are attracted to each one of these positives, if I end up putting a hole here, let me move this hole down just a little bit. Didn't quite get it exactly where it needs to be. I'll put the hole right here. Now those electrons are going to go right through that hole right there, and they're going to shoot out. Now, how do we liberate electrons? We could use a Van de Graaff generator, but as you've seen with me, we turn that thing on, it's going to arc all over the place. So inside here, this electron gun, let me draw you another view of what this electron gun might be. We can end up having a coil, and I'm going to end up using red mainly for temperature. Maybe I'll do it this way. So what this is really going to end up being, you just do a little aside here to show you what is in that electron gun. Think of a set of coils, and those coils are going to end up being connected to some kind of battery that I'll have down here. Take that down here, and then I'll end up putting a little battery symbol right there, right there. I don't need a lot of current for this, or a lot of voltage. Maybe make that just a little bit bigger. There we go, there's our battery. And that battery is going to end up giving us electrons through that wire. If I have sufficient resistance, they're going to get hot. And as it gets hot, because it's got some resistance, electrons tend to be so energetic, according to kinetic molecular theory, that they are going to boil off. So these electrons literally just end up leaving the atoms. Inside here, they feel this field, this F equals QE. There's a field because of these positives here, and they're going to accelerate in that direction at a very high rate of speed. Now I've got electrons that are zooming right through this plate. Now I'm going to make two other plates. I'm going to make a horizontal and I'll make a vertical. Let's see if I can do that. I'll do one plate right here. I'll do a horizontal like so. I'll make this look a little something like that. I'll put another plate up here. That looks like it. And then I'll put one up here, a little behind. Now these plates, I can also connect to a battery. And maybe on top, I can put some positive charges. Maybe on the bottom, I could put negative charges. It doesn't matter. Let me put some positives up here. I'll put a positive, positive, positive. And this other one, I'll put some negatives. So I'll put negative, negative, negative. Well, we know that there's going to be an electric field here, and that electric field is going to cause these electrons to end up interacting. So as they're coming along here, I've got field lines. Let me draw these down, going from my positive down to my negative. So you can see that we're using our electric field to essentially steer these electrons. Look, the electrons want to avoid the negatives. They're going to go up towards the positives, and you can see they're going to bend up. This is a lot like what we might have for a gravitational field. So think of if you had something and you were firing a projectile on Earth. We could end up saying, well, if I ended up having, and this is Earth down here, and it should be round, but whatever, and that's Earth, and it's got lots and lots of mass, well, we'd have a gravitational field that would be pulling down also. Now, the difference between masses and electrons is electrons tend to go against the field. But if I had a real gun, like a rifle, and I'm hunting, we could see that we're going to end up having that parabolic path. In this case, our parabolic path happens to be up. Here's our first set of plates, and again, I would connect that to some kind of battery over here. Maybe I could just draw that. This would be in the background, and then over here. And then I could control that. Maybe it would touch that plate, this one. Maybe I'd have some variable resistor here. And we'll get to resistors soon enough. But for right now, just understand that I'd be able to control this. And so maybe I'd have a little arrow going up like this. And then I'd go over to my battery. And so I'd have a negative, and then I'd have my positive. And then I'd have that connected to that plate right there. So I could end up putting little bits of charges on each of those plates just using a battery. And this would be maybe a knob that I could adjust. So if I wanted to put a greater amount of charge to have a greater effect, I could get this thing to swing up. Regardless, this thing is now going to be going in this direction. Now what I'm going to do is I'm going to use another set of plates. Instead of having horizontal plates, let's use a set of vertical plates. Maybe I need to make those a little bit bigger here. I'll make one plate here, and maybe I'll make it out here. Might be making it too big, but I think you'll get the general idea in a second here. I add one set of plates here, and let's say there's another set of plates behind them. This is stressing my artistic ability, but I hope everyone will get the idea. If I took this over here, I've got another set of plates right behind it, right here, like so. Now, let's say that I put the positive plates towards me. So I'll put a few positives on here. I could also use a battery for this. Doesn't take much. I'm just going to start putting some charges. And that means on this other plate, I'm going to end up having a few negatives. So as this is going between those two plates, if you're an electron, you want to go away from these. So look, I would have my field lines going in that direction. Oh, I guess I should make those black just to be consistent with the rest of what I'm doing. That looks bad now. But I want it to look as accurate as possible. All right, so let's see if I can fix these at all. Good enough. So now I can end up having my field lines going in this direction here. And because I have the field lines going in that direction, the electrons are going to end up bending away from the negative towards the positive. So look, the first set of plates, they go up a little bit, and then they're going to bend to the side. They're going to go over there. Now what I'll use is a piece of phosphorus, put some phosphorus on glass, and maybe I could make a giant screen. Usually they're circular, but maybe I'll just make it a big green screen for right now. And this green screen is what we often see on the old-time movies, things that maybe I'll make this bigger. Didn't realize that this diagram was going to get this big, but I think you're going to get the idea in a moment here. All right, let's just say that we had some green screen. If it were to hit this, now look, that electron beam is now going to be bending in this direction. Oh, I don't know why I had it going down. It's going to stay up. Went up like that. And so now they're going to end up bending inward and hit right there. And what we're going to see is a glowing mark. And so that's supposed to be more of a straight line. But this is our green screen. That looks rough. And we use green because phosphorus tends to glow in the dark. Phosphorescence. It tends to end up taking our electrons, bumping them up to a higher level. And so in the dark, they will continue to give off a little bit of light. Screen. Oh my. This is a tough marker. It's sticking to the board here. Screen. Okay. All right, so this whole thing is called an oscilloscope. And it is like a magic device. And notice we don't use any of our charge. We are just directing the charge. So this is an oscilloscope. And this oscilloscope can tell us the voltage that the charges have on it by using our plates. I have an oscilloscope, and I'll set that up in just a moment. All right, here's an oscilloscope. And I'll give you a little tour. First of all, these are modern in that they have circuit boards and things of that nature. There's a big transformer here, and this has not been plugged in for some time, but they can still give you quite a zap. So I'm going to make sure not to touch anything. And I would never encourage you to take one of these apart until after our course, and we learn how to discharge capacitors. Regardless, on this specimen, you can't see much. I had an older version, and it was great and spectacular. A little bit more dangerous, but it caught on fire the one time. It was so old. The oil in the caps leaked and caused a fire, so we had to get rid of that. But either way, you can't quite see, but here's my electron gun right here. The electronics here are going to end up giving us a very high voltage. Now, you might have needed 20,000, 30,000, 40,000 volts for an old style cathode ray tube, but now we can use a cold cathode. And we're only going to be talking about probably 500-600 volts is going to be enough once we use this thermionic emission, and that's really what it's called. Thermo, right? Temperature, ionic, ions, electrons, emission. They're going to be emitted off this, this little coil of wire there, thermionic emission. So they are going to boil off here, and in here I would end up having plates. Now, they're going to end up having different kinds of materials. We used to use lots and lots of lead because you didn't want any potential X-rays in case something went wrong escaping from here. But now, you know, you can't see anything anyhow, but you're going to end up having the little plates, and they would only be about a centimeter or two. You'd have your horizontal plates and then your other set of vertical parallel plates, and that beam would shoot over here onto this screen. Now what I'm going to do is I'm going to put all this back together. Now, just so you can see that I have wires going into those plates inside that's going to control how much, and I didn't bother drawing a battery on this one, but I'll show you the controls. But the first thing I need to do before I plug this in and show you is put the protective lid on. So I'll need a minute. All right. Now I plugged in my oscilloscope, and now we're ready to turn it on. Now this is going to use electricity to get that thermionic action so that we can get the electrons coming out here. Now the beautiful thing about this is, in terms of what we're measuring, it's not going to interfere at all. So we're going to use one of these lantern batteries, and these are 6 volts. Let's show you how this works. So the first thing I do is I turn this on, and it's got to warm up for a second. Now I'll put the beam in one place so it's not moving at first. See, there it is. So I've got a beam, and now to get it to go across the screen here, I'm going to end up having these 2 plates, the vertical plates, saying, okay, put positive on one side, negative on the other, and increase it over time. So the beam is going to end up bending. And then once it gets over here, there's a little person inside here that's going to end up switching the circuit on and off. And so it'll do this over and over. Of course, we use an electronic circuit. There's no being in here, but I could speed this up and maybe even make that a line. I can go faster and faster till it's a solid line. Now, when I put the battery on here, I'm going to use this probe. So there's a ground probe, and then there's also the positive probe. Now I'm going to end up, we're really going to use a battery here, and we're going to end up influencing our horizontal plates. So if I were to take this, first of all, I'm on, let me see what this reads. I'm on 2 volts per division. So you'll notice these blocks, that's a division, that's a division. Now I can always move these. I can say horizontally, I can adjust them, but I'll put them right at our x-axis, right at our origin. I think you can see that, and that's going to be at 0. So now if I take a 6-volt battery, I'll clip this onto the negative right here, and then I'll clip this onto the positive terminal, and lo and behold, it jumps up. So what I've done is I've just completed this circuit right here, and I've put 6 volts on here. The beauty of the oscilloscope is I'm not actually using any of the power of the battery. All I'm doing is I'm connecting it so the 2 plates get a little bit of charge on them. That's it. It's not like this charge goes anywhere or wears out or anything. So an oscilloscope is like a perfect voltmeter. And this is maybe the very best way to measure voltage. So what are oscilloscopes? Oscilloscopes use our electric fields to end up giving us our voltage. And I can use this for all kinds of different styles of circuitry. Now, the beauty of this is I can end up saying, I'm going to take this off. I'm going to take and position this down. Maybe I want a little bit more accuracy or precision in my measurement. And I'm going to take this to 1 volt per division. I can make sure it's calibrated. I'll put it right there. Now, each one of those blocks is going to be 1 volt, so I can end up putting this up here. And now you could see it's actually a little bit above 6 blocks. So I've got 1, 2, 3, 4, 5, 6. So I'm about 6.2 volts, whatever that is. It's hard for me to see right here. But that is our very first voltmeter. And this is a beautiful device. Most oscilloscopes nowadays are digital. I love the old school that has the CRT, that cathode ray tube, but they're kind of falling out of fashion. All right, let me clean this up and I'll show you the last thing. The oscilloscope is just a wonderful device, especially for measuring voltage. But this thermionic emission, let me write that up, thermionic emission is going to have limits. For instance, if I were to try to take the voltage of a Van de Graaff generator using an oscilloscope, it couldn't handle it. An oscilloscope, good quality one, might only go up to 600 volts. Let's show you how to do it for a Van de Graaff. I'll need to erase this. All right, we've met this Van de Graaff generator before. It's given me a few zaps. If I turn this on for a moment, and I don't want it to build up too much, but we know it's going to happen. It's going to build, it's going to build, it's going to build. How do we ever get the voltage of this? I certainly can't use a normal voltmeter. Let me see if I can draw this Van de Graaff. I'll put the dome here, and then maybe I'll put the center column here. I think we get the idea of what this machine does. All right, so I'll just put a VDG. Now, it's going to clearly build up more and more charges on here, and so these charges are going to end up having some voltage as we move away. We've already figured out and established it's going to end up having, the voltage is going to drop off as, I guess I should put a proportionality of 1 over the R as such. So it's proportional to 1 all over the radius. So we know at the edge of this Van de Graaff generator, if I were to make a graph of this, it's going to end up having this inverse function. And this axis over here would be our voltage, and this would be our distance or our radius. We could put D or our radius in that direction. We know it's going to drop off on each side in that manner. So I can draw another graph on this side. And of course, it'll drop off as some kind of inverse. That should be more curved. It shouldn't be a straight line. See if I can fix that a little bit. It doesn't drop off quite as an inverse squared. Now, the interesting thing is on the inside, and we'll have to explain this, the voltage essentially flatlines, and it's going to stay the same on this Van de Graaff. How do we figure out the voltage? That's what we were talking about. So here's one of the things that we know is air is going to start to break down from being an insulator to a conductor. We say the voltage, the breakdown voltage of air is about 3 million volts per meter. And so we could use our classic V equals ED, also known as V equals our ER. And if I know the radius of this dome, and this is about 9 centimeters, so I can use that right there. I could say, well, the voltage, the operating voltage of my VDG would be my 3 million, and I'll use my breakdown voltage here. So I could use 3 million volts per meter, and then I can end up multiplying it by the radius. And the radius here we said is 0.09 meters. So the voltage, the working voltage of that Van de Graaff generator would be about 270,000 volts. And so theoretically, that's the best I can come up with perfect conditions. Now that 270,000 volts is a lot, and as soon as you start ionizing the air, everything changes. It's that first arc that's really hard, but once you start ionizing the air, this thing's going to arc over and over again, and the overall voltage that it's going to take to end up jumping from your skin to you, the Van de Graaff to your skin is going to be much less, maybe 50,000, 100,000, and so on. But either way, this is a really nice idea, the idealized case of what the voltage of a Van de Graaff generator could be, and if I wanted to increase it, I need a bigger dome, because the larger the radius, the greater the voltage. One of the other things that's neat, and this is just a general rule, is that whatever the radius of the dome is, it's usually able to jump about that distance also. So that's just a general rule for Van de Graaff generators. All right, so look, we're able to see how electric fields not only are showing us forces, but now energy, and that energy per charge is voltage. And we now have ways that we can start talking about voltage either theoretically or how we're able to measure them. All right, that's your lesson for today. Thank you for watching another Idealized Science Institute video. We are a nonprofit organization. If you like what you've seen, be sure to like and subscribe. And if you want, leave a comment below. It's helpful to us. If you can financially support us, go to our website and hit the donate button. If you can't, simply by sharing these videos with other teachers and students in your life will be helpful. While at our website, you'll find that we have our Idealized Science Institute book that'll help you engage your students in dialogic discourse. There you'll also find we have a podcast where we break down educational research. We also have long-form lessons. If you're a teacher, you can watch these and go in the very next day and enact these. Along with this, we also have many other resources, including more quick quizzes. So thank you for watching, and we hope to see you in the next one.